Welcome to Thermodynamics. So thermo, heat, temperature, dynamics means things are changing. This is actually a really big and very important unit for AP chemistry and chemistry in general because it explains a lot of different things. It tells us when reactions occur, why they occur, and kind of what kind of energy is transferred in a reaction. Now, this is very, very deep, a very deep unit, so I encourage you to take good notes, ask questions, and practice, practice, practice. It's really easy to get left behind because there's a lot of information that's going to be thrown at you. And a lot of this actually goes against preconceived ideas about science and chemistry in general. There's going to be some terms that I throw at you that don't really match with what you thought they mean. So I need you to kind of forget those words and apply these new ones when we're talking about chemistry. And so here's a list of the different topics that we're going to be talking about. Let you read through those, but I want to draw your attention to this term heat. So this is one of those words that I was talking about that don't really match up with preconceived ideas. Heat means something different when we use it in chemistry or when we use it in science in general. And then enthalpy, entropy, and free energy are three different things we're going to talk about in this unit. You need to make sure that you understand what all three are and be able to separate them because they mean different things, but they might sound kind of the same. But in all, this is a really important unit because it explains a lot of different things. We use the heat energy to heat our homes, to drive our cars. In fact, every time we eat food, we're undergoing a combustion reaction. We're undergoing an exothermic reaction that generates our energy. Plants, on the other hand, are undergoing endothermic reactions where they take in energy and use it to cause reactions to occur. So there's a lot of different real-world connections with this. It explains a lot of things that we do every day. So let's define two terms that are very dear to this unit. Exothermic and endothermic. Both refer to either reactions or processes. You're probably familiar with the words and probably think you know what it means, but it goes a little bit more in depth than just the textbook definition. So exothermic, when you think of an exothermic reaction, you're probably thinking one that generates heat. And that's true, it is one that generates heat. But when you think of heat, you're probably thinking of temperature. So exothermic reactions are ones that feel hot. That's not always the case. A better definition is an exothermic reaction is one that releases energy. So it's not just one that produces hot or something that makes something warmer. It's just energy being released. Pretty obvious example of this would be like propane burning. If you've got a propane stove or a propane grill, you light it up, you flick it with a match, and it starts burning, and you feel that heat being released. That heat is energy that is being let go. So from the reaction of propane with air combusting, it is releasing energy, and that is an exothermic reaction. Another much less obvious exothermic process would be water freezing. So when you think about this, it probably doesn't strike you as an exothermic reaction because you think of exothermic reactions as things being you can't touch because they're so hot. Water freezing, though, that's really, really cold, but it's an exothermic process. Because when water goes from the liquid state to the solid state, it is releasing energy. Liquid has more energy than solid, and so therefore in order to get from this state to that state, energy would have to be lost. So that's an exothermic process as well, even though it feels cold to the touch. And so exo, release, like exoskeleton is on the outside, or exit. We have energy exiting from the molecules, from the chemicals that are in there. Endothermic, on the other hand, is energy being absorbed. So instead of the molecules releasing energy, in this case, they are taking energy in order to cause the process to occur. Now, endothermic reactions are a lot less common, but you usually think of them as something that feels cold to the touch, and sometimes that's true, but not always. An example then would just be like a cold pack, those ones where you break the thing in the middle, the chemicals combine, and it feels cold to the touch. Inside of that pack, the reaction that's taking place is an endothermic reaction. Another example of this would then be water boiling. And once again, this is probably one you wouldn't think of being endothermic because boiling water is very, very hot. But you're putting energy into the water. You turn on the stove, you supply energy to that liquid, and it turns into a gas. That means it is an endothermic process. So what I need you guys to do then is kind of forget about those definitions of hot versus cold. Instead, think about the energy. Everything in this unit is about tracing energy. Is it released? Is it absorbed? How much is released? How much is absorbed? All right, let's clear up two more terms then that people tend to get hung up on. So heat versus temperature. When you guys walk through my doors or when you're thinking about AP chemistry, I need you to forget what you know about these two words and apply them just this way. So heat is not necessarily hot. Heat is a form of energy that is measured in joules, and it's the form of energy that we're going to be talking about in this unit. And there's lots of different forms of energy. Motion is energy, waves are energy. This is just one of the different types. Then there's the word temperature. So temperature and heat, they kind of go hand in hand because heat energy does affect temperature, but it's not a direct correlation like we might think. Temperature instead is an average kinetic energy of atoms and molecules in a system. So if we take the motion of all those molecules and average them, that would give us what we feel, what we record as temperature. So this is more or less what we feel. This is what we talk about when we think of hot and cold. This right here, though, is a measure or a flow of energy. Heat, on the other hand, we can't always see and feel, so we can't think of it as just hot versus cold. That's what temperature is a measure of. A great analogy for this would be a mountaintop. Now, if you've ever been to a mountain on the summer and you're standing at ground level, it's probably going to be pretty warm, and so that's going to feel temperature hotter. Whereas if you're on top of the mountain, there's going to be snow around and it's going to feel a lot cooler. And so then if we apply everyday terms, we're going to think of the bottom of the mountain as hot and the top of the mountain as not hot. And so if I were to ask you to use the words heat, you would say there is more heat at the bottom than there is at the top, but that is not the case. The temperature is warmer and the temperature is cooler, but there is actually more heat at the top of a mountain than there is at the bottom of a mountain. And that's because heat is a measurement of energy. And if you think about the situation that we're looking at here, at the top of the mountain, you're going to be closer to the sun, and so there's going to be more energy being transferred from the sun up at the top of the mountain than there is at the bottom because less of it's going to get there. It feels hotter because there's more air molecules at the bottom of the mountain, and so the average temperature is going to be higher. Whereas at the top, when there's fewer air molecules, there's going to be less heat transfer, and so therefore you don't really feel it. So this is a good way to separate out heat versus temperature. Another thing to think about then is like a pot of water that's boiling on the stove. So you're constantly supplying it with heat, you're constantly supplying it with energy, and so it's boiling. But if you stick a thermometer in there, the temperature does not keep rising. It stays right at 100 degrees Celsius. So even though you are applying a continuous flow of energy, the temperature does not continuously rise because the energy is being absorbed and then transferred. So let's take a look at this graph. I failed to mention earlier, kinetic energy is the energy of motion. So things that are moving have kinetic energy. And this is directly related to temperature. This is kind of the best indicator of temperature. If you think of a solid where the molecules are stacked pretty tight, and they're in there, but they're just vibrating in place, that's a low amount of kinetic energy because there's a low amount of motion, as opposed to a gas where they're spread apart and they're flying everywhere. That would be high kinetic energy and therefore a higher temperature. That being said, what this chart shows then is the number of particles that are at a particular amount of kinetic energy. And this kind of helps us picture temperature and what it is. So if you look at the bell curve, and so this would be the center of each of those bell curves would be the average. And so the average kinetic energy for these particles, and there's some that are moving extremely slow, and there's some that are moving very, very fast. But on average, most of them are right here in the middle. So the average would be about 250 Kelvin, which would be the temperature that we feel, and that's about 23 degrees Celsius. So about room temperature. Even though there's molecules that are spread all over there, what we feel is the average. And for this larger curve, you see that it's about 500, and for a much larger curve, it's about 1,000. And actually, as kinetic energy increases, so does kind of the broad spectrum of all the different kinetic energies. So some in the green one are moving extremely fast, and some are hardly moving at all. But on average, it comes out to about 1,000 degrees Kelvin. So if we have two different systems or two different things that are at different temperatures, that means they have different amounts of energy, different amounts of heat. So if we put them in contact with each other, they will actually transfer and exchange energy from one to the other. So the one that has the higher energy, system 2 in this case, those molecules are going to be moving around a lot faster, higher kinetic energy. The molecules in system 2, a little bit cooler to the touch, is going to be moving slower. So this side will transfer energy to this side. So we're going to be going through an exothermic process here in that it's losing energy, and an endothermic process here in that it's gaining energy from system 2. Now they're going to continue to exchange heat until they have reached a point where they're the same. And at this point, they're still going to be transferring heat, but it's transferred back and forth at a constant rate, and so they stay at the same temperature with the same amount of energy. And so you notice that system 2 didn't give its energy to this guy and raise it to the same temperature. Instead, it lost some of its energy, so its temperature went down, and this one gained some of its energy, so its temperature went up. Overall, though, there is no change in the amount of energy possessed by this system. The energy lost by system 2 was gained by system 1. So overall, the amount of energy, if you add both of these together, stays the same. This is like when you sit down on a cold chair. First, it feels really cold, and what you're feeling is energy being transferred from your butt into the chair. But as you sit there for a while, the chair warms up, and it warms up because it is absorbing energy from your butt, so your butt is actually cooling down a little bit, the chair is warming up, and eventually they meet somewhere in the middle. And at that point, the system is at equilibrium. What we call this idea then of energy not being lost but just transferred is the conservation of energy. So it says that energy cannot be created nor destroyed. If something gets hotter, it's because it's gaining energy from somewhere. If something gets cooler, it's because it is losing energy to something. And it can take place in a variety of ways: a chemical reaction, a phase change, just a change in temperature. All of those result in energy being transferred into or out of the system. And keep in mind, we can't just feel something and tell which way the energy is going. Just because something's hot doesn't necessarily mean that it's giving away energy, or something that's cold doesn't necessarily mean that it's absorbing energy. We have to instead look at the system and think about how things are going to flow. And so here's two terms that we're going to be using a lot during this unit. The first is the system, which is the actual chemical reaction that's taking place, and then the surroundings, which is everything around it. So if we have a system that's going an exothermic process, that means it is losing heat. And it's not just losing heat in that it destroys it, it's sending that heat out to its surroundings. So we'd have the system, here's the chemical reaction, and the surroundings would be everything around it. So the air, person's hands, whatever it is.